Radiation physics, a phrase that can strike fear into the hearts of radiology students everywhere. Perhaps it's the abstract nature of invisible X-rays that cause their anxiety, or maybe it's the need to memorize formulae and have a grasp of algebraic functions. Either way, it's a subject that many learners have trouble with. One of the most commonly referred to aspects of radiation physics is the behavior of photons as they travel through space. You may be familiar with the operation of a flashlight. The cone-shaped beam of light travels out from the source, in this case a bulb, through space, gradually dispersing to the point that objects in the distance are no longer illuminated. And so it is with all forms of radiation originating from a single source, visible or not. It is a fundamental rule of our world that can be described using the inverse square law. It is the purpose of this tutorial to take some of the mystery out of its use. The inverse square law states that the intensity I of radiation is inversely proportional to the square of the distance d from the source of emission. This means that as photons travel away from their source toward a target, they spread apart in a cone-shaped beam. And the farther away the target is from the source, the fewer photons strike it, thus reducing the target's exposure. This is expressed as the intensity of the incident beam at the target. Before we get started with examples, here are some definitions. Please pause the video when needed. The basic form of the law is an equality stated as I1 over I2 equal to D2 squared over D1 squared. In order for us to use the law to solve for unknown values, we need to derive the equation to isolate the variables. First, let's look at the form for finding intensity based on distance. I2 needs to be isolated, so let's multiply both sides by I2. These variables cancel each other out on the left side, giving us this. Now we multiply both sides by the inverse of the distance proportion, d2 squared over d1 squared. These proportions cancel out on the right side of the equation, leaving us with I2 equal I1 times the quantity d1 squared over d2 squared. The law can also be derived to solve for distance. Starting with the inverse square law, we must first cross-multiply the equality, giving us I2 times d squared equal I1 times d1. We may then divide both sides by I2, allowing us to cancel variables on the left side. This leaves us with the formula d2 squared equal I1 times d1 squared over I2. Exposure to scatter radiation occurs when one stands too close to a patient receiving dose from the primary beam. Avoid scatter radiation by increasing your distance from the source. Suppose you are standing 1 foot away from an unsteady patient during an exam, and the scatter dose you can expect to receive at that distance is 1.3 rad. Calculate the dose from the same exposure if you stood 3 feet away from the patient. Use the equation for finding intensity. I2 equal I1 times the quantity d1 squared over d2 squared. Replace I1 with 1.3 rads, d1 with 1 foot, and d2 with the new distance, 3 feet. Simplify the equation. Now multiply 1.3 times the quantity 1 divided by 9 to get 0.14 rad. As you can see, a small increase in distance results in significant decrease to your dose. Occasionally, you will need to make changes to standard SID settings in order to accommodate the patient that arrives to the department in a wheelchair or gurney. As we have seen, an increase in SID will result in a decrease in patient exposure unless the technical factors are increased. Suppose a patient arrives in a large wheelchair for an exam of the upper back. Due to the width of the chair, you cannot move the tube into the standard 40-inch SID and decide to make the exposure at 56 inches instead. Given that the standard exposure at 40 inches would be 80 kVp at 23 Mass, what would the new Mass be at 56 inches without increasing kVp? Once again, we will need to solve for the intensity at the new distance. Replace I1 with 23 Mass, D1 with 40 inches, and D2 with the new distance 56 inches. Now simplify the equation and multiply 23 times the quantity 1,600 divided by 3,136 to get 11.73. This is the new intensity at 56 inches. If you want to get the same amount of penetration at 40 inches, you need to increase the mass at the control panel. But by how much? This can be done with the conversion factor derived from I1 and I2. Since I1 was 23 and I2 is 11.73, you must divide 23 by 11.73 to get 1.96. This conversion factor is then multiplied by I1, 23 and 23 Mass to get 45.09, or 45 Mass for the new setting. Even though we only touched on some of the basic uses for the inverse square law, I hope that you have learned some of the best ways that we use it in radiology. The study of physics can leave you in a jumble, but success is worth the hard work. Keep up your studies and I know you'll nail it.